Unearthing Earth's Climate, What Ancient Ice Cores Tell Us. The concept of delving into Earth's past by reading the frozen chronicles of its glaciers was not a sudden revelation, but rather a gradual dawning in the collective consciousness of scientific inquiry. The journey into the heart of ancient ice began not with a sophisticated drill, but with a simple, yet profound, realization that the immense ice sheets of Greenland and Antarctica were more than just static, lifeless expanses of white. They were in fact dynamic, layered archives, each stratum a frozen page of history, meticulously recording the climatic and atmospheric conditions of its time. Early glaciologists of the 19th and early 20th centuries, intrepid explorers and thinkers, laid the theoretical groundwork. They observed the seasonal accumulation of snow, its transformation into firn, and ultimately its compression into dense glacial ice. This process, they hypothesized, would preserve a vertical timeline of past snowfalls, much like tree rings record the passage of years. The initial forays into this frozen world were fraught with peril and limited by rudimentary technology. Early attempts to extract ice samples were often crude, involving hand-driven augers and saws, yielding only shallow, disturbed cores that offered tantalizing but incomplete glimpses into the recent past. These pioneering efforts, however, were crucial in proving the fundamental principle that ice contained a record of the past waiting to be deciphered. The true revolution in ice core science, however, would have to wait for the mid-20th century and the convergence of technological advancement and a growing urgency to understand Earth's climate system. The International Geophysical Year of 1957-58 served as a major catalyst, fostering international collaboration and providing the impetus for ambitious polar research projects. It was during this period that the first deep ice cores were successfully drilled, penetrating hundreds of meters into the Greenland ice sheet. These early cores, though still relatively shallow by modern standards, were a revelation. They provided the first continuous, high-resolution records of past climate, confirming the layered nature of the ice and revealing distinct annual signals. Scientists could now literally count back the years, layer by layer, and analyze the physical and chemical properties of the ice at each point in time. The analysis of these early cores was initially focused on stable isotopes of oxygen and hydrogen in the water molecules of the ice. This groundbreaking technique, based on the principle that the isotopic composition of precipitation is dependent on temperature, allowed scientists to reconstruct past temperature fluctuations with remarkable precision. The resulting temperature records from Greenland revealed a climate history far more dynamic and variable than previously imagined, with abrupt shifts and significant long-term trends. This was the first time humanity had a direct, empirical record of past climate change, a record that extended back thousands of years before the advent of instrumental measurements. The success of these early drilling projects in Greenland spurred further exploration and the development of more advanced drilling technologies capable of reaching greater depths and recovering higher quality cores. The focus of research also expanded beyond temperature reconstructions to include the analysis of dust, chemical impurities, and most importantly, the tiny bubbles of ancient air trapped within the ice. The realization that these air bubbles were pristine samples of past atmospheres, containing a direct record of past greenhouse gas concentrations, would once again revolutionize the field and elevate ice core science to the forefront of climate research. The genesis of glacial archives was a story of human curiosity, perseverance, and the relentless pursuit of knowledge in one of the planet's most extreme environments. It was a journey that transformed our understanding of Earth's climate history from a matter of speculation to a field of precise, empirical science, laying the foundation for all the profound discoveries that were to follow. The silent, frozen world of the polar ice sheets had begun to speak, and its stories of a dynamic, ever-changing planet were just beginning to be told. The early pioneers of ice core science had not just drilled into ice, they had opened a window into the deep past, a window that would reveal the intricate workings of our planet's climate system and our own place within it. This foundational period of exploration and discovery set the stage for a new era of scientific inquiry, one that would see scientists from around the world converge on the polar regions to unlock the secrets held within the ice. The once barren landscapes of Greenland and Antarctica were now seen for what they truly were, invaluable libraries of Earth's history, their frozen shelves holding the keys to understanding our planet's past, present, and future climate. The initial challenge of simply reaching and surviving in these remote locations gave way to the more intricate challenge of extracting and interpreting the information they held. The development of specialized drills, clean handling protocols, and sophisticated analytical techniques became paramount, each innovation pushing the boundaries of what was possible and allowing for a more detailed and nuanced reading of the icy archives. The discovery that glacial ice contained perfectly preserved samples of ancient air trapped in tiny bubbles was a watershed moment in the history of climate science. It transformed ice cores from simple climate proxies into direct archives of the Earth's past atmospheric composition. Suddenly, scientists were no longer limited to inferring past conditions from indirect evidence. They could now directly measure the concentration of greenhouse gases like carbon dioxide and methane as they existed thousands or even hundreds of thousands of years ago. This was a quantum leap in our ability to understand the intricate relationship between the atmosphere and climate. The process by which these atmospheric samples are captured is a slow and delicate one. As snow falls and accumulates on the surface of an ice sheet, air fills the spaces between the individual snow crystals. As more snow piles on top, the underlying layers are compressed, and the snow gradually transforms into a denser material called firn. The air-filled spaces remain interconnected for a time, allowing for some exchange with the atmosphere above. However, as the firn is buried deeper and the pressure continues to increase, the interconnected channels eventually pinch off, and the air becomes permanently trapped as individual bubbles within the solid ice. This process of bubble entrapment typically occurs at depths of 50 to 100 meters below the surface, meaning the air in the bubbles is younger than the surrounding ice. Understanding and accounting for this age difference is a critical aspect of ice core analysis. The painstaking process of extracting and analyzing the air from these bubbles is a marvel of modern analytical chemistry. In a laboratory setting, under carefully controlled conditions to avoid contamination with modern air, a small piece of the ice core is placed in a vacuum chamber and then either melted or crushed to release the trapped ancient air. The release gas is then passed through a series of sophisticated instruments, such as gas chromatographs and mass spectrometers, which can precisely measure the concentrations of various gases. The initial analyses of these ancient air samples yielded astonishing results. For the first time, scientists could see a direct, unambiguous correlation between past atmospheric carbon dioxide concentrations and global temperatures, as reconstructed from the ice's isotopic composition. The data from the Vostok ice core in Antarctica, for example, which provided a record extending back over 400,000 years, showed that CO2 and temperature rose and fell in near-perfect synchrony through multiple ice ages and interglacial periods. This provided powerful, direct evidence for the role of greenhouse gases in driving long-term climate change, confirming a hypothesis that had been debated for decades. Furthermore, the ice core records revealed that pre-industrial levels of carbon dioxide were remarkably stable for thousands of years, hovering around 280 parts per million. This stable baseline provided a stark contrast to the dramatic and unprecedented rise in CO2 concentrations that began with the Industrial Revolution and continues to this day. The ice cores, in essence, provided the smoking gun for anthropogenic climate change, showing that the recent increase in greenhouse gases was far outside the range of natural variability observed over hundreds of thousands of years. The analysis of methane in the trapped air bubbles told a similar story, revealing a close link between methane concentrations, climate, and human activity. Methane levels were also shown to have been relatively stable in the pre-industrial era, with natural fluctuations linked to the extent of wetlands, a major natural source of the gas. The ice cores also captured the dramatic increase in methane concentrations in the modern era, driven by agriculture, fossil fuel extraction, and other human activities. Beyond carbon dioxide and methane, the ancient air bubbles have also provided valuable information about other atmospheric components, such as nitrous oxide and various isotopes of nitrogen and oxygen. These measurements have helped scientists to reconstruct past changes in biogeochemical cycles, atmospheric circulation, and the global carbon cycle. The whispers of ancient air, once locked away in the frozen heart of the ice sheets, have spoken volumes about the Earth's climate system. They have provided a long-term perspective on climate change, revealing the natural rhythms of our planet and the profound impact that human activities are now having. The direct empirical evidence from the ice cores has been instrumental in shaping our modern understanding of climate change and has provided the scientific foundation for international climate policy and action. The silent, tiny bubbles, each a miniature time capsule, have delivered a clear and urgent message from the past, a message that continues to resonate in the ongoing scientific and societal conversation about our planet's future. Deep within the serene, layered stillness of the polar ice sheets lies a dramatic and often violent record of Earth's past volcanic activity. Each significant eruption, no matter where it occurs on the globe, has the potential to leave an indelible mark in the ice, a chemical fingerprint that allows scientists to reconstruct a detailed history of volcanism stretching back through the millennia. This frozen archive of fire provides invaluable insights not only into the frequency and magnitude of past eruptions, but also into their profound impact on the global climate system. When a volcano erupts with explosive force, it spews vast quantities of gases, ash, and other particles high into the atmosphere. If the eruption is powerful enough to inject this material into the stratosphere, the layer of the atmosphere above the weather, it can be transported around the globe by high-altitude winds. The most significant of these volcanic emissions, from a climate perspective, is sulfur dioxide gas. In the stratosphere, sulfur dioxide is converted into tiny droplets of sulfuric acid, which form a reflective haze that can persist for several years. This volcanic aerosol layer acts like a global sunshade, scattering incoming solar radiation back into space and causing a temporary cooling of the Earth's surface. As these sulfuric acid aerosols and fine volcanic ash particles eventually fall out of the atmosphere, a portion of them is deposited on the surface of the polar ice sheets along with the annual snowfall. As this snow is buried and compressed into ice, it preserves a distinct layer of volcanic fallout, a chemical anomaly that stands out against the background of pristine ice. Scientists can detect these volcanic layers in ice cores through a variety of methods. One of the most common techniques is to measure the electrical conductivity of the ice. The presence of acidic volcanic material, primarily sulfuric acid, significantly increases the conductivity of the ice, creating a sharp spike in the electrical conductivity profile of the core. These spikes serve as precise time markers, allowing scientists to date the ice core with great accuracy and to correlate records from different locations. In addition to electrical conductivity, scientists can also perform detailed chemical analysis of the ice to identify specific volcanic tracers, such as sulfate, chloride, and tiny glass shards known as tephra. The unique geochemical composition of the tephra can often be matched to a specific volcanic source, allowing for the precise identification of the eruption that produced it. By analyzing the amount of sulfate deposited in a volcanic layer, scientists can estimate the magnitude of the eruption and the amount of sulfur dioxide that was injected into the stratosphere. This information is crucial for understanding the potential climate impact of the eruption. The ice core record of volcanism has revealed a history of cataclysmic events that have had a profound influence on human history. For example, the massive eruption of Mount Tambora in Indonesia in 1815, the largest in recorded history, is clearly marked in both Greenland and Antarctic ice cores. The resulting year without a summer, in 1816, led to widespread crop failures, famine, and social unrest across the northern hemisphere. The ice core data has also helped to identify other major climatically significant eruptions, such as the eruption of Laki in Iceland in 1783 and the massive eruption of the Samalas volcano in Indonesia in 1257, which is believed to have triggered the onset of the Little Ice Age. Beyond these major events, the ice cores provide a continuous, long-term record of volcanic activity that has allowed scientists to study the role of volcanism as a natural driver of climate variability on a range of timescales. This long-term perspective is essential for distinguishing natural climate fluctuations from those caused by human activities. The decoding of volcanic eruptions from the icy archives is a testament to the interconnectedness of the Earth system. It reveals how events in one part of a world can have far-reaching consequences, and how the seemingly static ice sheets are, in fact, dynamic recorders of some of the planet's most dramatic and powerful events. The fiery breath of volcanoes, once thought to be lost to the winds of time, is now being meticulously reconstructed from the frozen depths, providing a clearer picture of our planet's turbulent past and a better understanding of the forces that continue to shape its climate. Each acid spike in the ice is a memorial to a past cataclysm, a story of darkness and cooling that rippled across the globe, a story now being read with stunning clarity in the silent, frozen library of the poles. This ability to pinpoint and quantify past volcanic events not only helps in understanding past climate, but also provides critical data for validating and improving climate models, ensuring they can accurately simulate the climate response to large-scale aerosol injections, a key uncertainty in future climate projections. The Sun, the ultimate source of energy for Earth's climate system, is not a perfectly constant star. Its energy output varies over time, driven by complex magnetic processes within its interior. These variations, though small, have the potential to influence our planet's climate. For centuries, scientists have sought to understand the nature of solar variability and its impact on Earth. The ice cores, with their remarkable ability to preserve a record of past environmental conditions, have provided a unique and powerful tool for investigating the Sun's cyclic dance and its terrestrial consequences. One of the primary ways in which solar activity is recorded in the ice is through the production of cosmogenic radionuclides in the Earth's atmosphere. These are rare isotopes that are produced when high-energy cosmic rays, particles from deep space, collide with the nuclei of atoms in the atmosphere, the Earth's magnetic field, and the solar wind, a stream of charged particles flowing from the Sun, act as a shield, deflecting many of these cosmic rays. When solar activity is high, the solar wind is stronger, and the Earth's magnetic shield is more effective, leading to a decrease in the production of cosmogenic radionuclides. Conversely, when solar activity is low, the solar wind is weaker, and more cosmic rays are able to penetrate the atmosphere, increasing the production of these isotopes. Once produced, these cosmogenic radionuclides, such as beryllium-10 and carbon-14, are transported through the atmosphere and eventually deposited on the Earth's surface, including the polar ice sheets. By measuring the concentration of beryllium-10 in ice cores, scientists can reconstruct a continuous, high-resolution record of past solar activity stretching back thousands of years. This record has revealed the existence of several well-defined solar cycles, including the famous 11-year Schwabe cycle, as well as longer-term variations in solar activity. The ice core records have been instrumental in identifying periods of unusually low solar activity, such as the Maunder minimum, 1645 to 1715, and the Sporer minimum, 1460 to 1550. These grand solar minima have been linked to periods of cooler climate in some regions of the world, particularly in the northern hemisphere, and are thought to have been a contributing factor to the Little Ice Age. The precise mechanisms by which small changes in solar output can influence global climate are still a subject of active research. One proposed mechanism is that changes in ultraviolet (UV) radiation from the Sun can affect the chemistry of the stratosphere, leading to changes in atmospheric circulation patterns that can then propagate down to the surface. Another possibility is that changes in solar activity could influence cloud formation, which in turn would affect the amount of solar radiation that reaches the Earth's surface, while the direct warming effect of Changes in total solar irradiance is thought to be relatively small compared to the warming from greenhouse gases. The ice core record suggests that the sun may play a more subtle, but still significant role in modulating regional and long-term climate variability. The study of the sun's cyclic dance as recorded in the ice is a fascinating intersection of astrophysics, nuclear physics, and climate science. It is a reminder that the Earth's climate is not just a product of terrestrial processes, but is also influenced by our planet's place in the wider cosmos. The silent, frozen layers of the ice sheets have captured the faint whispers of distant solar storms and the subtle rhythms of our star's magnetic heart, providing a long-term perspective on solar-terrestrial relationships that is essential for a complete understanding of our planet's climate system. The beryllium-10 record, locked in the ice, provides a crucial baseline of natural solar forcing of the climate, allowing scientists to more clearly distinguish the powerful signal of anthropogenic forcing in the modern era. As we look to the future, understanding the full spectrum of solar behavior, from its regular 11-year cycle to the possibility of future grand minima, is a key piece of the climate puzzle, a piece that has been brilliantly illuminated by the ancient ice. The ice cores of Antarctica and Greenland offer a unique and unparalleled window into the history of Earth's atmosphere, providing a direct and continuous record of greenhouse gas concentrations that stretches back hundreds of thousands of years. This long-term perspective is absolutely crucial for understanding the natural dynamics of the climate system and for contextualizing the profound atmospheric changes that have been wrought by human activity in the modern era. Before the advent of ice core science, our knowledge of past atmospheric composition was limited to the instrumental record, which began only in the mid-20th century. This provided a mere snapshot in time, offering little insight into the long-term trends and natural variability of greenhouse gases. The ice cores, with their tiny, trapped bubbles of ancient air, changed everything. They provided the missing backstory, a prequel to the modern drama of anthropogenic climate change. The data from these frozen archives has revealed a remarkably consistent picture of greenhouse gas concentrations over the past 800,000 years, a period that encompasses multiple ice ages and warm interglacial periods. During the cold glacial periods, when vast ice sheets covered much of the northern hemisphere, carbon dioxide concentrations were consistently low, hovering around 180 parts per million. ppm. In contrast, during the warmer interglacial periods, CO2 levels rose to around 280 ppm. This tight coupling between carbon dioxide and global temperature, observed through 8 glacial cycles, stands as one of the most important and unequivocal findings of ice core research. It provides powerful, direct evidence for the fundamental role of greenhouse gases in regulating the Earth's climate. The ice core records for methane, another potent greenhouse gas, tell a similar story, with concentrations fluctuating in close synchrony with the glacial-interglacial cycles. These natural variations in greenhouse gases were driven by slow, long-term changes in Earth's orbit, known as Milankovitch cycles, which altered the distribution of solar energy reaching the planet's surface. These orbital changes initiated a cascade of feedbacks within the climate system, including changes in ocean circulation, biological productivity, and the global carbon cycle, which in turn modulated the atmospheric concentrations of greenhouse gases, amplifying the initial climate response. The ice core record also provides a stable, long-term baseline against which to compare the recent, human-caused increase in greenhouse gases. For the entirety of the 800,000-year record, carbon dioxide concentrations never rose above 300 ppm. This natural ceiling was shattered in the early 20th century, and CO2 levels have been climbing at an accelerating rate ever since. Driven by the burning of fossil fuels, deforestation, and other industrial activities, the current atmospheric concentration of CO2 is now over 420 ppm, a level unprecedented in at least the last 800, a level that is, in fact, higher than it has been for several million years, long before the evolution of modern humans. This dramatic and undeniable departure from the natural range of variability is a clear and sobering testament to the scale of the human impact on the Earth's atmosphere. The ice cores, in essence, have provided the before picture, the pristine pre-industrial state of the atmosphere. This has allowed scientists to state with a high degree of confidence that the recent increase in greenhouse gases is not a natural phenomenon, but a direct consequence of human actions. Furthermore, the historical perspective from the ice has been instrumental in building and validating the climate models that are used to project future climate change. By demonstrating that these models can accurately simulate the climate of the past, as recorded in the ice, we can have greater confidence in their ability to predict the consequences of our ongoing greenhouse gas emissions. The frozen bubbles of ancient air, once a scientific curiosity, have become one of the most powerful and important sources of information in the ongoing global conversation about climate change. They have provided the historical context, the scientific underpinning, and the clear, unambiguous evidence of our planet's altered atmospheric state. The ice has spoken, and its message is clear. The atmospheric changes of the industrial era are a profound and unprecedented departure from the natural rhythms of our planet, a departure with far-reaching consequences for the future of our climate. Within the long and detailed climate narratives provided by Greenland ice cores, a series of dramatic and perplexing climate fluctuations stand out, a rhythmic pulse of warming and cooling that punctuated the last glacial period. These events, known as Dansgaard-Oeschger (DO) events, represent some of the most abrupt and large-scale climate shifts ever recorded, and they remain one of the most fascinating and intensely studied enigmas in paleoclimatology, named after the pioneering ice core scientists Willy Dansgaard and Hans Oeschger, who first identified them. DO events are characterized by a rapid warming of the northern hemisphere, often by as much as 10 to 15 degrees Celsius in Greenland, occurring over the course of just a few decades. This warm phase, known as an interstadial, would then persist for several centuries to a few millennia before a much slower, gradual cooling returned the climate to full glacial conditions. This cycle of abrupt warming followed by slow cooling repeated itself more than 25 times during the last ice age, from about 115,000 to 11,700 years ago. The sheer speed and magnitude of these warming events are staggering. They represent a fundamental shift in the state of the climate system, a flicking of a switch from a cold, glacial mode to a much warmer, near-interglacial state, and back again. The signal of DO events is most pronounced in the Greenland ice cores, but their influence was far-reaching, with corresponding climate changes observed in marine sediment cores from the North Atlantic and even in records from the Southern Hemisphere, including Antarctic ice cores and terrestrial archives in Asia and South America. The leading hypothesis for the cause of DO events centers on changes in the Atlantic Meridional Overturning Circulation, AMOC, a large-scale system of ocean currents that transports warm, salty water from the tropics to the North Atlantic. This ocean conveyor belt releases vast amounts of heat to the atmosphere, playing a crucial role in regulating the climate of the Northern Hemisphere. It is thought that the AMOC can exist in at least two different states, a strong, on mode, similar to today's circulation, and a weak or off mode. During the last ice age, the AMOC was likely in a weaker state than it is today. The theory suggests that DO events were triggered by a sudden and rapid reorganization of the AMOC, flipping it from its weak, glacial mode to a stronger, more active state. This would have dramatically increased the northward transport of heat, leading to the abrupt and intense warming observed in Greenland and the surrounding regions. The triggers for these sudden shifts in ocean circulation are still not fully understood, but they're thought to be related to the complex interplay of freshwater inputs into the North Atlantic from melting ice sheets, changes in sea ice cover, and internal instabilities within the ocean atmosphere system. After a period of warmth, a gradual buildup of freshwater in the North Atlantic, perhaps from melting icebergs or changes in river runoff, may have eventually slowed the AMOC down again, tipping the climate back into its cold, glacial state. The Dansgaard-Oeschger enigma is a stark reminder that the Earth's climate system is not always linear and predictable. It is capable of rapid and dramatic reorganizations with the potential for large and widespread impacts. The existence of these abrupt climate shifts in the recent geological past has raised concerns about the potential for similar events to occur in the future as the climate system is pushed into a new state by anthropogenic warming. While full-scale DO event is not considered likely in the near future, the study of these past events provides a crucial cautionary tale. It highlights the existence of tipping points in the climate system, thresholds that, once crossed, can lead to rapid and potentially irreversible changes. The intricate dance between ice, ocean, and atmosphere that drove the DO cycles of the past continues to this day, and the ice cores, with their exquisitely detailed record of these ancient climate dramas, provide an invaluable natural laboratory for understanding the complex and often surprising behavior of our planet's climate. Unraveling the full story of the Dansgaard-Oeschger enigma is a key priority for climate scientists, as it holds the promise of a deeper understanding of the fundamental processes that govern climate stability and the potential for abrupt change in a warming world. In the layered saga of the last ice age, inscribed within the deep-sea sediments of the North Atlantic are stark, anomalous bands of rock fragments that speak of colossal and catastrophic events. These layers, first identified by the German marine geologist Hartmut Heinrich, are the telltale signs of massive discharges of icebergs from the Laurentide ice sheet, the vast expanse of ice that once covered much of North America. These Heinrich Events, as they have come to be known, represent some of the most dramatic and far-reaching climate disruptions of the last glacial period, and their discovery has opened up a new chapter in our understanding of the dynamic and often violent interplay between ice sheets and the global climate system. Heinrich Events are characterized by the deposition of thick layers of ice-rafted debris on the ocean floor. As icebergs calved off the edge of the Laurentide ice sheet, they carried with them rocks and sediment that had been eroded from the landmass beneath the ice. These icebergs then drifted out into the North Atlantic, and as they melted, they released their rocky cargo, which then sank to the bottom of the ocean, forming a distinct layer of terrestrial sediment amidst the fine-grained marine ooze. The sheer scale of these events is difficult to comprehend. They involve the discharge of immense armadas of icebergs, a veritable flood of ice into the North Atlantic, causing a significant and rapid rise in global sea level. 6 major Heinrich events have been identified during the last glacial period, occurring at irregular intervals of several thousand years. These events are often associated with the coldest phases of the Dansgaard-Oeschger cycles, suggesting a close link between the two phenomena. The prevailing theory is that Heinrich events were caused by an inherent instability within the Laurentide ice sheet itself. As the ice sheet grew larger, its base would have been warmed by the geothermal heat from the Earth below. This, combined with the immense pressure of the overlying ice, could have led to the melting of the ice at its base, creating a slippery layer of water that allowed the ice sheet to surge forward and release vast quantities of icebergs into the ocean. This binge-purge cycle of slow growth, followed by rapid collapse, is a key feature of the Heinrich event hypothesis. The climatic consequences of these massive iceberg discharges were profound and widespread. The infusion of vast amounts of fresh, cold water into the North Atlantic would have had a dramatic impact on ocean circulation. It is believed that Heinrich events caused a near-complete shutdown of the Atlantic Meridional Overturning Circulation, AMOC, the ocean conveyor belt that transports heat to the northern hemisphere. This would have led to a severe and widespread cooling across the North Atlantic region, exacerbating the already frigid conditions of the Ice Age. The effects of Heinrich events were not limited to the North Atlantic. The disruption of the AMOC would have had a cascading effect on global climate patterns. The shutdown of the ocean conveyor belt would have altered the distribution of heat around the globe, leading to a bipolar seesaw effect with cooling in the north and warming in the south. Indeed, evidence from Antarctic ice cores shows that periods of warming in the southern hemisphere often coincided with Heinrich events in the north. The story of Heinrich's glacial surges is a powerful illustration of the active and often unpredictable role that ice sheets can play in the climate system. They are not just passive responders to climate change. They can also be powerful agents of change, capable of triggering large and abrupt shifts in global climate. The The study of these past events provides a crucial long-term perspective on the stability of modern ice sheets in a warming world, as the Greenland and Antarctic ice sheets continue to melt at an accelerating rate. The lessons from the past serve as a stark reminder of the potential for rapid and dramatic changes in our climate system. The rocky layers on the bottom of the Atlantic, the silent witnesses to ancient glacial catastrophes, have given us a profound and unsettling glimpse into the immense power of ice and the complex, interconnected nature of our planet. Understanding the dynamics of these past glacial surges is not just an academic exercise. It is a critical component of our efforts to predict and prepare for the future impacts of climate change. Just as the world was emerging from the icy grip of the last great ice age, and a warming trend seemed to be firmly established, the climate of the northern hemisphere took a sudden and dramatic turn. In climatic reversal of stunning speed and severity, temperatures plummeted, and glaciers that had been in retreat began to advance once more. This abrupt return to near-glacial conditions, which began around 12,900 years ago and lasted for approximately 1,200 years, is known as the Younger Dryas, named after an alpine wildflower, Dryas octopetala, that flourished in the cold, tundra-like conditions that prevailed across Europe at the time. The Younger Dryas is one of the most well-studied and enigmatic episodes in recent climate history, and it serves as a powerful reminder of the potential for abrupt and nonlinear climate change. The evidence for this dramatic cold snap is preserved in a wide range of paleoclimatic archives, including ice cores, lake sediments, and ocean cores. The Greenland ice cores, in particular, provide a high-resolution record of this event, showing a rapid drop in temperature of as much as 15 degrees Celsius in a matter of decades. This was accompanied by a significant increase in dust and a decrease in snow accumulation, indicating a colder, drier, and windier climate. The impact of the Younger Dryas was most pronounced in the North Atlantic region, but its effects were felt across the globe. The cooling in the north was mirrored by changes in precipitation patterns in the tropics and a slight warming in the southern hemisphere, consistent with the bipolar seesaw pattern of climate change. The leading hypothesis for the cause of the Younger Dryas is a massive and sudden influx of fresh water into the North Atlantic Ocean, which disrupted the Atlantic Meridional Overturning Circulation, AMOC. The most likely source of this fresh water was the catastrophic draining of Lake Agassiz, a vast glacial lake that once covered a large part of central North America. As the Laurentide ice sheet retreated at the end of the Ice Age, it acted as a dam, holding back an immense volume of meltwater in Lake Agassiz. It is thought that this ice dam suddenly broke, releasing a torrent of fresh water into the Arctic Ocean and from there into the North Atlantic. This massive infusion of buoyant freshwater would have effectively put a lid on the North Atlantic, preventing the sinking of the dense, salty water that drives the AMOC. The resulting shutdown of the ocean conveyor belt would have cut off the supply of warm water to the North Atlantic, plunging the region back into a deep freeze. The Younger Dryas had a profound impact on the ecosystems and human societies of the time. The rapid and severe cooling led to the widespread extinction of large mammals, such as the woolly mammoth and the mastodon, and is thought to have been a major factor in the transition from a hunter-gatherer lifestyle to the development of agriculture in the Fertile Crescent of the Middle East, as people sought more reliable food sources in a changing climate. The end of the Younger Dryas was as abrupt as its beginning. Around 11,700 years ago, the climate of the Northern Hemisphere warmed with breathtaking speed, returning to the warmer conditions of the early Holocene in a matter of years to decades. This rapid warming is thought to have been caused by the restarting of the AMOC as the freshwater influx ceased and the ocean circulation system reorganized itself. The Younger Dryas stands as a stark and compelling example of a climate tipping point. It demonstrates that the climate system can be pushed into a new state with surprising speed, and that the consequences can be dramatic and far-reaching. The story of this ancient cold snap, locked in the ice and other natural archives, is not just a fascinating tale from the distant past. It is a crucial lesson for the present It highlights the vulnerability of our climate system to sudden shocks and underscores the importance of understanding the complex and often unpredictable interactions between ice, ocean, and atmosphere as we navigate the challenges of a warming world. The Younger Dryas is a ghost of climate future, a powerful reminder that the path of climate change is not always smooth and gradual, and that the potential for surprises is very real. Following the tumultuous and abrupt climate shifts that marked the end of the last ice age, including the dramatic Younger Dryas cold snap, the Earth's climate system settled into a new and remarkably stable state. This period, which began around 11,700 years ago and continues to the present day, is known as the Holocene epoch. For the entirety of this time, a period that encompasses the whole of recorded human history and the rise of civilization, the global climate has been exceptionally stable, a stark contrast to the wild swings and rapid changes of the preceding glacial period. The ice cores from both Antarctica and Greenland provide an exquisitely detailed and continuous record of the Holocene's climate, and they are the primary source of our understanding of this prolonged period of climatic tranquility. The isotopic records from the ice show that global temperatures, after the initial rapid warming at the start of the Holocene, have fluctuated within a relatively narrow range of about 1 to 2 degrees Celsius. This stability is a key feature of the Holocene and is thought to have been a crucial enabling factor for the development of agriculture, the growth of permanent settlements, and the flourishing of complex human societies. The early part of the Holocene, from about 9,000 to 5,000 years ago, is often referred to as the Holocene climatic optimum. During this time, global temperatures were slightly warmer than they are today, and the climate was generally wetter and more stable. This period of warmth was driven by orbital factors, specifically a configuration of the Earth's orbit that resulted in more solar radiation reaching the northern hemisphere during the summer months. The ice core records from Greenland show that the ice sheet was smaller during this time, and that summer temperatures were several degrees warmer than in the 20th century. Following the Holocene climatic optimum, the Earth's climate entered a long and gradual cooling trend, driven by slow changes in the Earth's orbit. This cooling trend was punctuated by a series of smaller, century-scale climate fluctuations, but none of these came close to the magnitude of the Dansgaard-Oeschger events or the Younger Dryas. The ice cores have been instrumental in identifying and characterizing these more subtle climate variations of the Holocene, such as the 8.2 Ka event, a brief but significant cooling episode that occurred around 8,200 years ago, and is thought to have been caused by the final drainage of the glacial lakes of North America. The remarkable stability of the Holocene climate is a testament to the complex interplay of various components of the Earth system, including the oceans, the atmosphere, the ice sheets, and the biosphere. It appears that during the Holocene, the climate system entered a stable sweet spot, a mode of operation that was resilient to the kind of large-scale reorganizations that characterize the ice ages. This stability, however, should not be taken for granted. The ice core records also show that the Holocene has not been entirely without its climatic ups and downs. The medieval warm period, a time of relatively mild temperatures in some parts of the world from about 950 to 1250 AD, and the subsequent Little Ice Age, a period of cooler and more variable climate that lasted until the mid-19th century, are both clearly recorded in the ice. These events, though significant, were regional rather than global in scale, and were much smaller in magnitude than the climate shifts of the past. The story of the Holocene's stable climate, as told by the ice, provides a crucial long-term context for understanding the climate of the present day. It has established a baseline of natural climate variability, a benchmark against which we can measure the profound and unprecedented changes that are now being driven by human activities. The ice core records show that the warming of the past century is far outside the range of natural variability observed during the Holocene, and that the rate of warming is many times faster than any natural warming event in the past 11,700 years. The Holocene has been a unique and precious gift, a period of climatic grace that has allowed human civilization to prosper. The ice cores, with their silent, frozen testimony, have revealed the fragility of this gift and have issued a stark warning about the potential consequences of pushing our planet's climate out of the stable state that has nurtured us for so long. The long, peaceful summer of the Holocene is now being threatened by a new and powerful force of our own making, and the ice is bearing witness to this profound and perilous transformation. The long and relatively stable climate of the Holocene was not entirely without its fluctuations. Within this extended period of climatic calm, two notable multi-century climate anomalies stand out in historical and paleoclimatic records: the medieval warm period and the Little Ice Age. The ice cores, with their high-resolution, year-by-year chronicles of past climate, have been instrumental in characterizing these events, helping to place them in a long-term context and to unravel their underlying causes. The medieval warm period, also known as the medieval climate anomaly, was a period of relatively mild temperatures in some parts of the world, lasting from approximately 950 to 1250 AD. The evidence for this warmth comes from a variety of sources, including historical accounts of Viking colonization of Greenland and the cultivation of wine grapes in England, as well as from natural archives like tree rings and sediment cores. The ice cores from Greenland and parts of Antarctica also show evidence of a modest warming during this time. However, the ice core data, along with other paleoclimatic records, has revealed that the medieval warm period was not a globally uniform event. While some regions, such as the North Atlantic and parts of Europe, experienced significant warmth, other areas, including parts of the tropical Pacific, were actually cooler than average. This complex and patchy pattern of temperature change suggests that the medieval warm period was not caused by global forcing like an increase in greenhouse gases, but rather by a reorganization of atmospheric and oceanic circulation patterns. It is thought that a persistent positive phase of the North Atlantic Oscillation, a major mode of atmospheric variability, may have played a key role in the warming of the North Atlantic region during this time. Following the medieval warm period, the climate of the Northern Hemisphere, in particular, began to cool, ushering in the period known as the Little Ice Age. This was not a true ice age, but rather a period of cooler and more variable climate that lasted from about 1300 to 1850 AD. The Little Ice Age was characterized by the advance of mountain glaciers in many parts of the world, colder winters, and significant impacts on human societies, including crop failures, famine, and the abandonment of the Viking settlements in Greenland. The ice core records provide a detailed picture of the Little Ice Age, showing a clear cooling trend and a series of distinct cold snaps. The causes of the Little Ice Age are thought to be complex and multifaceted, with a combination of natural factors likely playing a role. The ice cores have provided crucial evidence for two of the main proposed drivers. Firstly, a decrease in solar activity, as indicated by the low levels of beryllium-10 in the ice, is thought to have contributed to the cooling. Two major grand solar minima, the Spore minimum and the Maunder minimum, occurred during the Little Ice Age. Secondly, an increase in volcanic activity, as recorded by the spikes of acidity in the ice, also played a significant role. A series of large volcanic eruptions, including the massive eruption of Samalas in 1257, would have injected large amounts of sunlight-reflecting sulfate aerosols into the stratosphere, causing a temporary but significant cooling of the Earth's surface. The study of the medieval warm period and the Little Ice Age, as illuminated by the ice cores, provides several important lessons for our understanding of the climate system. Firstly, it demonstrates that natural climate variability can be significant on multi-century timescales, and that regional climate can change in complex and sometimes surprising ways. Secondly, it highlights the role of natural forcings such as solar activity and volcanism in shaping our climate. Finally, and most importantly, it provides a crucial context for understanding the warming of the 20th and 21st centuries. The ice core records, along with a wealth of other data, show that the recent warming is far outside the range of natural variability observed during the Holocene, including the medieval warm period. The speed and global extent of the modern warming are unprecedented, and the ice core data on greenhouse gases clearly points to human activity as the primary cause. The tales of Vikings and vanished colonies, of frozen rivers and advancing glaciers, are not just historical curiosities, they are a vital part of a long and complex story of our planet's climate, a story that is being told with ever-increasing clarity from the frozen depths of the ice sheets. The dawn of the Industrial Revolution in the late 18th and early 19th centuries marked a profound turning point in the history of human civilization and in the history of the Earth's atmosphere. For the first time, human activities began to release greenhouse gases and other pollutants into the atmosphere at a scale sufficient to alter its composition and, ultimately, to change the planet's climate. The ice cores, with their meticulously preserved layers of snow and trapped air bubbles, provide a direct and unambiguous record of this dramatic and ongoing transformation. They have captured the chemical fingerprint of industrialization, a clear and indelible mark in the frozen archives of our planet. Before the Industrial Revolution, the atmospheric concentrations of greenhouse gases, as recorded in the ice cores, had been remarkably stable for thousands of years. Carbon dioxide levels had hovered around 280 parts per million, and methane concentrations were also at a stable pre-industrial baseline. The ice cores show that this long period of atmospheric stability began to change around the year 1800. The air bubbles trapped in the ice from this period onward reveal a steady and then accelerating increase in the concentrations of both carbon dioxide and methane. This increase is in lockstep with the rise of industrial society and the large-scale burning of fossil fuels. The isotopic composition of the carbon in the trapped CO2 provides further damning evidence, a smoking gun, that links the increase to the combustion of coal, oil, and natural gas. But the icy imprint of the Industrial Revolution is not limited to greenhouse gases. The ice cores also record a dramatic increase in other industrial pollutants. The layers of ice from the 19th and 20th centuries contain elevated levels of sulfate, a byproduct of the burning of sulfur-rich coal. This increase in sulfate deposition, particularly in the northern hemisphere, is a clear marker of the widespread industrial activity and the resulting acid rain that plagued many parts of North America and Europe. The ice also records the global spread of other industrial pollutants, such as heavy metals like lead. The lead concentrations in Greenland ice cores, for example, show a dramatic increase that parallels the rise of industrial production and the use of leaded gasoline in the 20th century. The ice has even captured the faint radioactive signature of the atomic age, with distinct layers of radioactive isotopes from the atmospheric nuclear weapons testing of the mid-20th century. These radioactive layers have served as valuable time markers, helping to precisely date the upper sections of the ice cores. The story told by the ice is one of a profound and rapid shift in the Earth's atmospheric chemistry, a shift that is far outside the range of natural variability observed over the past 800,000 years. The ice cores provide a stark and undeniable before and after picture, a clear demarcation between the pre-industrial world and the new, human-altered atmosphere of the modern era. This long-term perspective has been absolutely critical in establishing the scientific consensus on anthropogenic climate change. It has allowed scientists to say with a very high degree of confidence that the recent changes in our atmosphere and climate are not part of a natural cycle, but are instead a direct consequence of our own actions. The silent, frozen layers of the polar ice sheets have become an unimpeachable witness to the dawn of a new geological epoch, the Anthropocene, an era in which human activities have become the dominant force of change on our planet. The Industrial Revolution, a period of unprecedented human ingenuity and progress, has left a complex and troubling legacy in the ice. It is a legacy of a fundamentally altered atmosphere, a legacy that continues to unfold and to shape the future of our planet, the ice cores, with their precise and detailed record of this transformation, provide a powerful and sobering reminder of the far-reaching consequences of our industrial society and the urgent need to transition to a more sustainable future. The chemical whispers of the first steam engines and the belching smokestacks of the industrial age are now permanently etched into the frozen heart of our planet, a silent testament to a world in transition. For much of scientific history, the vast ice sheets of Greenland and Antarctica were considered to be sterile, lifeless deserts of ice and snow. It was assumed that the extreme cold, high pressure, and lack of liquid water and nutrients would make these environments inhospitable to life. However, in recent decades, advances in microbiology and the analysis of ice cores have led to a stunning and revolutionary discovery. The polar ice sheets are not sterile at all, but are in fact teeming with a diverse and surprisingly active community of microorganisms. This hidden biosphere, locked in a state of suspended animation within the ice, has opened up a whole new frontier in the study of life in extreme environments and has profound implications for our understanding of the Earth system. The evidence for life in the cryosphere comes from the direct examination of ice core samples under the microscope and from the use of sophisticated molecular techniques to detect the presence of microbial DNA and RNA. These studies have revealed a remarkable diversity of microorganisms, including bacteria, archaea, fungi, and even viruses, all perfectly preserved within the frozen matrix of the ice. These microbes are not recent contaminants, but are ancient organisms that were deposited on the ice sheet surface along with snow and dust thousands, or even hundreds of thousands, of years ago. Once buried within the ice, these microorganisms enter a dormant, frozen state, but they are not dead. They are capable of surviving in this state for immense periods of time, and some have even been successfully revived in the laboratory after being extracted from ancient ice. The concentrations of these microbes are generally low, but in some layers of the ice, particularly those with high dust content, the numbers can be surprisingly high. The discovery of this ancient, frozen biosphere has raised a number of fascinating and important questions. How do these organisms survive in such an extreme environment? What are the metabolic processes that allow them to endure the cold and pressure for so long? And what role, if any, do they play in the Earth's biogeochemical cycles? Studies have shown that some of these microbes are capable of carrying out metabolic activity at temperatures well below freezing, and that they may play a role in the cycling of nutrients and gases within the ice sheet. The study of life in the ice has also opened up new avenues for astrobiology, the search for life beyond Earth. The ice-covered moons of Jupiter and Saturn, such as Europa and Enceladus, are considered to be some of the most promising places to look for extraterrestrial life in our solar system. The discovery of a thriving microbial ecosystem within Earth's own ice sheets has provided a powerful terrestrial analog for these icy worlds and has given scientists a better understanding of the potential for life to exist in such extreme, frozen environments. The ancient DNA and RNA preserved in the ice also provide a unique and invaluable record of past ecosystems. By analyzing the genetic material of the trapped microorganisms, scientists can reconstruct the history of microbial life on Earth, and can even identify ancient pathogens. The study of icebound viruses, in particular, is a rapidly developing field with the potential to shed light on the evolution of viral diseases and the risk of ancient pathogens being released as the ice sheets melt in a warming world. The discovery of a hidden world of microscopic life within the cryosphere has fundamentally changed our perception of the polar ice sheets. They are no longer seen as inert, lifeless landscapes, but as dynamic ecosystems, vast frozen archives of biological as well as climatic history. The silent frozen world of the ice has revealed itself to be a surprisingly lively place, a testament to the tenacity and adaptability of life on Earth. The study of these ancient, frozen microbes is still in its infancy, but is already yielding profound insights into the limits of life and the intricate connections between the biosphere and the cryosphere. The smallest of organisms locked in the oldest of ice are telling a new and unexpected story about the history and diversity of life on our planet. The ice core records from Antarctica have provided an unparalleled view of Earth's climate and atmospheric history, a continuous narrative stretching back an astonishing 800,000 years. This record from the Epica Dome Sea Ice Core has been transformative, revealing the rhythmic dance of 8 glacial-interglacial cycles and the tight coupling between greenhouse gases and global temperature. But as profound as this record is, it leaves a major scientific question unanswered. What happened before 800,000 years ago? There is a tantalizing gap in our direct knowledge of Earth's climate history, a period known as the mid-Pleistocene transition, when the dominant rhythm of the ice ages mysteriously shifted from a 41,000-year cycle to a 100,000-year cycle. Unraveling the cause of this fundamental shift in the planet's climate system is one of the holy grails of paleoclimatology, and the key to solving this mystery is believed to be locked away in the oldest ice on Earth, thus a new and ambitious scientific quest is underway. The search for a continuous ice core record that extends back 1.5 million years or more. Finding this ancient ice is an enormous challenge. The ideal location for such a core would be a place where the ice sheet is very thick, the geothermal heat flow from the Earth below is low, and the snowfall rate is minimal. These conditions allow for the preservation of ancient, deep layers of ice that have not been melted by the heat from the bedrock below. Search for the oldest ice is focused on the vast, high-altitude plateau of East Antarctica, one of the coldest and most remote places on the planet. Teams of scientists from around the world are using a combination of radar surveys and sophisticated modeling to identify potential drilling sites. Ice-penetrating radar can be used to map the internal layers of the ice sheet and to measure its thickness, while models of ice flow and temperature can help to predict where the oldest ice is most likely to be found. Several promising sites have been identified, and a new international drilling project beyond epoch oldest ice is now underway. The goal of this project is to retrieve a continuous ice core that extends back at least 1.5 million years. The technical challenges of such a project are immense. It will require drilling down through more than 3 kilometers of solid ice. In one of the harshest environments on Earth, the process of drilling and recovering such a long an ancient core will take several years to complete. The potential scientific payoff, however, is equally immense. A 1.5 million-year-old ice core would allow scientists to directly measure the concentration of greenhouse gases in the atmosphere during the mid-Pleistocene transition. This would provide a definitive test of the leading hypothesis for the shift in the Ice Age cycle, which posits that a gradual long-term decline in atmospheric carbon dioxide was the primary driver. The ancient ice would also provide a wealth of other information about the climate of this critical period, including temperature, dust, and aerosols. This would allow for a much more complete understanding of the complex feedbacks and interactions that led to this fundamental change in the Earth's climate state. The quest for the oldest ice is more than just a scientific adventure. It is a journey into the deep past of our planet, a quest to understand the fundamental rhythms of our climate system. The knowledge gained from this ancient ice will not only help us to unravel the mysteries of the past, but will also provide a crucial long-term perspective on our own human-caused climate change. By understanding how and why the climate has changed in the past, we can better predict how it will change in the future. The silent, ancient layers of the East Antarctic ice sheet hold the key to this understanding, and the international scientific community is now poised to unlock their secrets. The quest for the oldest ice is a testament to the enduring power of human curiosity and the relentless drive to explore the unknown, a journey that promises to rewrite the early chapters of our planet's climate story. The ice core records from the polar regions have provided a wealth of information about past climate change, but they also hold crucial clues about the future. Two of the most significant and concerning aspects of modern climate change are polar amplification and the associated rise in global sea level. The ice cores, through their detailed records of past warm periods, offer a unique and invaluable long-term perspective on these phenomena, providing a glimpse into how the polar regions and the world's oceans might respond to a warmer world. Polar amplification is the phenomenon whereby the polar regions are warming at a much faster rate than the rest of the planet. This is a robust feature of modern climate change, and it is also a consistent feature of past warm periods as recorded in the ice. The isotopic records from Greenland and Antarctic ice cores show that during past interglacial periods, when global temperatures were only slightly warmer than today, the polar regions experienced a much greater degree of warming. This amplified response is due to a variety of feedback mechanisms that are particularly strong in the polar regions. One of the most important of these is the ice albedo feedback. As sea ice and snow cover melt, they expose the darker ocean and land surfaces below. These darker surfaces absorb more solar radiation, leading to further warming and more melting. This creates a powerful positive feedback loop that amplifies the initial warming. The ice cores have helped to quantify the strength of this feedback in the past, providing a crucial benchmark for climate models. The consequences of polar amplification are far-reaching. The rapid warming of the Arctic is leading to the thawing of permafrost, the release of additional greenhouse gases, and profound changes in polar ecosystems. It is also accelerating the melting of the Greenland and Antarctic ice sheets, which is the primary driver of modern sea level rise. The ice cores provide a direct and sobering record of how the ice sheets have responded to past warming. By analyzing the thickness of the annual layers in the ice, scientists can reconstruct past changes in snowfall and ice accumulation. By comparing the records from different locations, they can also infer changes in the overall size and shape of the ice sheets. The data from past warm periods, such as the Eemian interglacial about 125,000 years ago, is particularly illuminating. During the Eemian, global temperatures were about 1 to 2 degrees Celsius warmer than in the pre-industrial era, a level of warming that we are rapidly approaching today. The ice core and other paleoclimatic data show that during this time, the Greenland ice sheet was significantly smaller than it is today, and that global sea level was about 6 to 9 meters higher. This provides a stark and unsettling glimpse into the potential long-term consequences of our current warming trajectory. Suggests that even a modest and sustained warming could be enough to trigger a significant and irreversible melting of the Greenland and West Antarctic ice sheets, leading to a catastrophic rise in sea level that would inundate coastal cities and displace hundreds of millions of people around the world. The story of polar amplification and sea level rise, as told by the ice, is a story of cause and effect, of a powerful and sensitive system that is now being pushed into a new and dangerous state. The ancient ice, with its long memory of past warm worlds, has provided a clear and urgent warning. It has shown us that the polar regions are the canary in the coal mine of climate change, and that the fate of the world's coastlines is inextricably linked to the fate of the great ice sheets. The lessons from the past are written in the ice for all to see, a silent and frozen testament to the immense power of our planet's climate system and the profound responsibility that we now bear for its future. The ice cores, with their rich and detailed chronicles of Earth's past climate, have become an indispensable tool for the development and validation of the complex computer models that are used to project future climate change. These climate models are the foundation of our understanding of the future climate, and their reliability is of paramount importance for policymakers and society as a whole. The ice cores provide a unique and powerful way to test the performance of these models, to assess their strengths and weaknesses, and to improve their ability to simulate the complex workings of the Earth system. One of the most important ways in which ice core data is used in climate modeling is for model validation. By comparing the output of a climate model for a past period with the actual climate of that period, as reconstructed from the ice cores, scientists can assess how well the model is able to simulate real-world climate processes. For example, a climate model can be run for the last glacial maximum, about 21,000 years ago, and its simulated temperatures, snowfall rates, and atmospheric composition can be compared with the data from the ice cores. If the model is able to accurately reproduce the conditions of the past, it gives us greater confidence in its ability to predict the future. The ice core data has been particularly valuable for testing the ability of climate models to simulate abrupt climate change. The records of Dansgaard-Oeschger events And the Younger Dryas, with their rapid and large-scale climate shifts, provide a stringent test for the models. While some models are now able to simulate these types of events, there are still significant challenges in accurately capturing their timing, magnitude, and regional expression. The ice cores have also been crucial for improving our understanding of the fundamental physics and chemistry of the climate system, which in turn leads to better climate models. The direct measurements of past greenhouse gas concentrations from the ice, for example, have been essential for quantifying the sensitivity of the climate to changes in CO2. The ice core records of dust and aerosols have helped to improve the representation of these important components of the climate system in the models. And the data on past ice sheet behavior has been used to develop and refine the ice sheet models that are a critical component of modern Earth system models. As we look to the future, the ice cores will continue to play a vital role in climate modeling and prediction. The ongoing quest for the oldest ice will provide new data from a time in Earth's history when the climate was very different from today, offering a new and challenging test for our models. The continued analysis of existing ice cores with ever more sophisticated analytical techniques will yield new insights into the intricate workings of the climate system, the story of ice cores and climate. Modeling is a powerful example of the synergy between observation and theory in science. The hard-won data from the frozen ends of the Earth has provided the ground truth, the empirical evidence that has guided the development of our theoretical understanding of the climate system. And the climate models, in turn, have provided the framework for interpreting the ice core data and for extrapolating its lessons into the future. The silent, frozen archives of our planet have given us a profound and detailed understanding of our climatic past, but their most important contribution may yet be to come. By providing the key to understanding and predicting the future of our climate, the ancient ice of Greenland and Antarctica is offering us a chance to make more informed choices about the path we take, a chance to navigate the challenges of a warming world with a clearer view of what lies ahead. The future is not yet written, but the past, as chronicled in the ice, has given us the tools to read the signs and to shape a more sustainable future for generations to come. Thank you for joining our deep dive into Earth's climate history. The stories locked in ancient ice are a stark reminder of our planet's dynamic past and a critical guide for our future. Subscribe for more journeys into the heart of science and discovery. Stay curious and see you next time.